In this video, we will be covering some of the basic concepts of what controls the physical environment on Earth. We'll start out by differentiating between the terms weather and climate. We will then cover some of the basic underlying factors that determine climate at a large scale, and then again, perhaps at a local scale. So first, some terms that you've probably heard before, weather and climate. Weather is a very specific term. It refers to current conditions. So for instance, if you looked up the weather report for today and you found that the high was 86, there was a 20% chance of rain, that would be weather. So it covers things like temperature, how hot or cold it is, precipitation, humidity, cloud cover, things that are going on at this particular moment. Climate, on the other hand, is a more long-term concept where we're looking at how weather has changed over time on average, measured over very long periods of time, so decades or even longer. So for instance, here is a climate average chart for Newark. It says that in July, the typical high is around 88, typical low is around 65, and we get about 8 days of rain out of the month of July, whereas in December tends to be colder, the high tends to be around 46, the low around 28 degrees, and we get about 7 days of rain. So remember, these are averages over long periods of time. This does not mean that you might not get a day in July that is over 88, so for sure, we've had days in July that are in the 90s, but on average, the high tends to be around 88. We also might get a warm day in December or a very cold day in December that are not reflected in this. So climate, long-term descriptions of weather that looks at cycles. So today we're going to be talking mainly about climate. So what controls these long-term patterns that we see? Why is it warmer in July in Newark and colder in December? And why do we get around 8 to 6 days of rain throughout the year? First off, one of the major things that determines climate is differences in how solar radiation affects the Earth. So if you look at the Earth, we live on a sphere, and so at the equator, the surface of the Earth is pointed roughly directly at the sun. Whereas at the poles, the surface of the Earth is pointed away from the sun. So the sun rays strike directly at the equator, whereas they strike at an angle at the North Pole and the South Pole. What this means is that the same amount of energy that's striking a small surface area at the equator is covering a much larger surface area at the poles. So what this ends up causing is that temperature is much higher near the equator than it is at the poles. And we get a graph such as this. So as you get further away from the equator, so degrees latitude increases, temperature goes down. Now we see that there is a plateau, a flat part between 0 and 20 degrees latitude. We'll talk about that a little bit more later. That has to do with cloud cover, and that has to do with one of the next concepts that we're going to be talking about. So temperature is warmer at the equator and colder at the poles, something that shouldn't be too surprising for most of you. Okay. Because so much energy hits the Earth at the equator, it causes something else to happen. As the solar energy hits the Earth at the equator, it causes air to rise. So warm air rises. As that warm air rises, the moisture that's in that warm air condenses, and we get lots of cloud cover. And because pressure is lower at higher altitudes, as that air, that moist air rises, it begins to release its moisture, and we get a lot of rain at that point. Now that air needs to go somewhere. It can't just constantly be rising at the equator up into the upper atmosphere, and so it gets pushed north and south. And you see in this figure, letter B is the air being pushed either north or south of the equator. Eventually, because temperature is cooler in the upper atmosphere, that air condenses as it cools and sinks. And it tends to sink around 30 degrees north and 30 degrees south on average. Because it released all of its rain, all of its water at the equator, this descending air is very, very dry. And so you get very, very dry conditions at 30 degrees north, 30 degrees south. The air then returns to the equator, so flows back towards the equator, replacing the air that is rising. And as it's moving towards the equator, it starts to pick up moisture along the way. It then repeats this cycle, where it's back to A again, where it's warming, rising, dropping its water, being pushed north and south. It's letter B. It then cools and descends, letter C. It's very dry at that point, so it starts picking up moisture as it flows back towards the equator, D again. So these are cycles, and then we actually see multiple of these cycles, and we'll cover that a little bit later. There's another of these cells further north, and there's another one near the northern pole. So we think there's about 3 in northern hemisphere and 3 in the southern hemisphere. And we'll look at that in a graphic in a little bit. Okay, so heavy rain at the equator, drier conditions at 30 degrees north, 30 degrees south. You also have winds going in 2 different directions. You'll notice the winds in the upper atmosphere, part B of this figure, are headed from the equator north and south, and the winds near the surface are headed from 30 degrees north and 30 degrees south towards the equator. So that's letter D there. Okay. While all this is happening, the Earth is spinning. And as the Earth spins, this creates another impact. So winds that are headed north or south actually don't travel directly north or south. And the reason for this is as the Earth spins, the Earth will spin beneath those traveling winds. So if you look at this graphic, this is a graphic of an imaginary person kicking a ball or throwing a ball from the North Pole towards the equator. And they're intending to throw it in a direct path to the equator. But as the ball is in the air, the Earth rotates, and therefore rather than the ball landing on the eastern side of South America, the ball would actually land on the western side of South America. So the ball seems like it's traveling in a westerly direction, even though it was thrown directly south. This is what's called the Coriolis effect. So as winds move either towards the equator or away from the equator, they appear to be curved, they appear to deflect either to one side because of the rotation of the Earth. Because we have some wind moving north and we have some wind moving south, was shown in that last graphic, we end up with some wind being deflected west and some winds being deflected east. And if we look at the effect of this, here, when you look towards the equator, so right at the equator at 0 degrees, remember wind is going from 30 degrees towards the equator, those winds are going to be deflected west. Now north of 30 degrees, winds are actually traveling away from the equator, and that causes the opposite thing to happen. The winds are actually deflected to the east. And we'll look at that in more detail in class. So these winds near the equator, so just focus on between 30 degrees north and 30 degrees south for now. These winds are what are called the trade winds. And you'll notice that the trade winds in the northern hemisphere are coming from the northeast, and the trade winds in the southern hemisphere are coming from the southeast. And these are actually the winds that sailors used to use to travel across the Atlantic Ocean. They're called the trade winds because they allowed them to travel from, for instance, Africa to the Americas. And so if you wanted to go from Africa to the Americas, you would want to travel between 30 degrees north and 30 degrees south because the winds would be taking you from east to west. If, on the other hand, you wanted to travel back the other direction, you would want to travel further north, between 30 degrees north and 60 degrees north, and winds would then be pushing you in the opposite direction. So sailors had to be very conscious of these winds. Remember, this is due to the Coriolis effect, because the rotating nature of the Earth causes winds to be deflected as they're traveling in those cells. One more thing that impacts climate is the angle of the Earth and its rotation around the sun. So the Earth is not straight up and down, which means that as it rotates around the sun throughout the year, sometimes portions of the Earth will be pointed more directly at the sun, and other times of year, portions of the Earth will be pointed slightly away from the sun. This changes the location of those cells. So the sun rays do not strike most directly, always directly at the equator. During June, July, and August, the sun is pointing most directly at an area just north of the equator. During December, so December, January, February months, the sun is pointing most directly at an area slightly south of the equator, which means that the warmest part of the Earth is not always at the equator. There's part of the year where it's just north of the equator, and there's part of the year where it's just south of the equator. So there's seasonal variation in temperature, and you probably know this as well. So during the months of June, July, and August, because we live north of the equator and the sun is striking directly just north of the equator, we have slightly warmer temperatures than we do during December, January, and February, where we are actually further away from the most direct sunlight. And so we get impacted by how far away we are from where the sun strikes most directly. So if we look at these cells again, remember the Hadley cell listed here is the one that we've been focusing on. That cell will actually move north in June, July, and August. And so rather than the center of that cell being at 0 degrees, the center of that cell is slightly north, which causes those rain clouds to travel a little bit north. So parts of the Earth that are just north of the equator will have very wet summers. So June, July, and August will be very wet. In December, January, and February, however, those cells move further south. And so rather than the really dry part of the Earth being at 30 degrees north, the dry zone travels a little bit further south. And so areas that were wet in the summer will actually have drier winters. And so we get the seasonality to rainfall. So it's not always wet, though there are parts of the Earth that are always in the wet zone. And it's not always dry, though there are parts of the Earth that are always in the dry zone. So we end up with these patterns where we have a band that's always wet right around the equator. We have bands just north and south of the equator that have a wet and a dry season. And then if we go a little bit further north and south, we have bands that are always dry. And those bands repeat themselves as we go further north and further south. Okay, so this is what influences large-scale climate. So we've seen several things. One, we have uneven heating of the Earth due to the sun striking more directly in certain parts and less directly in other parts. We have that uneven heating causing these cell formations where we get rain in one portion and dry parts in other portions. We then have the Coriolis effect, which causes wind to be deflected east or west. And then we have seasonalities, the angle of the Earth causing those cells to move north and south during different times of year. Now, the last thing I'm going to cover in this video is smaller scale climate influences. So these are called regional climate influences. So you might notice that different parts of the US, for instance, that may not be any further north or south from each other will have different climates. And there's several things that could influence that. First thing is, how close are you to the ocean? Now, the ocean is a large mass of water, and water takes a lot of energy to heat and cool. So it takes a very long time to heat up and cool down water, whereas land tends to heat up and cool down much faster. So, as a result of this, we think about summer days. During the summer, the land will heat up fairly rapidly as it's exposed to the sun. The water will heat up much more slowly. Because of this, the air around the land tends to be warm, and the air around the water tends to be cool. This leads to a similar effect as we saw with those Hadley cells. Over land now, the warm air rises, forms clouds, and then blows offshore in the upper atmosphere, and cool air from the ocean replaces that warm air that has risen out of the way, bringing cool air onto land. So you end up with breezes from the ocean coming on land. What that does is that actually brings cool air onto land and keeps that land close to the ocean fairly cool. Whereas if you were further away from the ocean, you wouldn't have that cool air blowing onto the warm land, and you'd just end up with a pretty warm climate. The opposite happens at nighttime, where you'll get the ocean will stay warmer, the land will cool down very rapidly, and you'll get breezes from land onto water, and so you get a reversal of this directionality of wind flow. So you may notice this if you go to the shore during the summer. Notice that during the day, breezes tend to come off the water, and they tend to be fairly cool. At night, the breezes will go the opposite direction. They'll come from land and flow onto water because the land is cooler than the water. So what this tends to do is it tends to, one, moderate temperature in areas that are close to water. It also creates slightly different climate patterns because you might get different patterns of rainfall depending on how close you are to a water source, as in you may get rain clouds at different times of year than you would get if you were further away from those water sources. Second thing that really impacts local climates are altitude. So mountains create large changes in climate because as you go higher up in elevation, you have less air pressure and lower density of air molecules, which means that it takes a lot more energy from the sun to warm the air at higher altitudes, just simply because there's less molecules of air to absorb that energy. Therefore, as you go up in altitude, we tend to get lower temperatures. So you can see here that we have very higher temperatures, 23 degrees Celsius at 1,000 meters, whereas we've decreased to 10.5 degrees Celsius at 3,000 meters. So altitude tends to lead to decreased temperature, increased altitude. Another thing that happens with mountains is something called a rain shadow effect. So similar to what we see in those cells, as air rises, it tends to drop water. Same thing happens when air rises because it's being forced up by a mountain. So if you have air that is blowing from shore onto a mountain, like in this graphic here, and it goes up the mountain slope, as it goes up in altitude, the pressure is going to be decreased, and that air will not be able to hold as much moisture as it could at lower altitudes. Therefore, it releases its moisture on the side of the mountain that it is flowing up. So we get a lot of rain on that side of the mountain. Now, as the air goes down the other side, similar to what happens at 30 degrees north and 30 degrees south, that descending air is very dry. It's picking up moisture from around it, leading to very dry conditions. So you end up with one side of the mountain, the side facing the winds, that has lots of rain, perhaps lush vegetation, and then the opposite side of the mountain that has less precipitation and is much drier, and you end up with perhaps desert-like conditions on the other side of the mountain. Okay, so all of these factors lead into climate conditions on Earth, whether it's large-scale patterns like the Hadley cells, like Coriolis effect, or smaller-scale patterns like this rain shadow effect, or like the proximity to ocean effects. In the next video, we will be covering how these different climatic patterns lead to differences in distributions of organisms on Earth.